Hello, I'm Seema and welcome to part 22 and the last part of the chapter, the solid state. I thought before I proceed to the next chapter that I'm planning to do, that is alcohols, phenols and ethers, I should discuss these in-text questions with you in the end, just to clarify everything that I've already explained. And I would encourage you to watch the videos that are before this in the chapter in order to really be very clear beforehand, so that this only kind of acts as the final layer of clarifying the concepts to you. The questions, let's come straight to the questions. These are in-text questions from that is chapter 1, question 19 to chapter 1, question 24. The first question is 1.19, that is 1.19. What type of defects can arise when a solid is heated? Which physical property is affected by it and why? When a solid is heated, if it has some component which may be volatile, which can escape through the solid, it may leave vacancies. So when you heat up a solid, the chances of some of the constituent particles evaporating or moving out of the kind of surface of the solid in order to create vacancies which may then be occupied. If, let us say, they are ions, there are chances, for example, if you have an oxide, the oxygen may evaporate, thereby creating vacancies. So the kind of defect that may arise when you heat up a substance is a vacancy defect. And which physical property will be affected by it? If one of the substances or one of the components or constituent particles leaves the solid, the mass of the solid decreases, but the size does not change. So mass per unit volume changes or decreases. In other words, what is mass per unit volume? It is density. So what type of defect is created? A vacancy defect is created. A vacancy defect is created. The answer to this would be a vacancy defect is created. And which physical property will be affected? It will be density. And why would density decrease? The density would decrease as mass decreases. Since some of the substance has moved out, the mass of the solid decreases, and therefore density is the physical property that is affected. What type of stoichiometric, now this is question 1.20, 1.20. What type of stoichiometric defect is shown by zinc sulfide and silver bromide? Zinc sulfide shows Frankel defect. Frankel defect. Okay. What happens in the Frankel defect is that when you have a difference in the size of the cation and the anion, the cation is usually smaller. So what happens? The cation, being smaller, moves away or slips away from its lattice site. And when it moves away from the lattice site, since the size difference between the cation and anion is large, the interstitial spaces would also be larger. So the cation is so small that it can slip from its lattice site and occupy an interstitial site, thereby creating a vacancy defect from where it moved and an interstitial defect where it entered or where it finally came and sat. So that kind of a defect is known as Frankel defect. So zinc sulfide shows Frankel defect, and silver bromide shows both Frankel and Schottky defects. Frankel defect, again, the difference between the sizes of silver and bromine is large. Silver is much smaller than a bromine atom, and therefore silver slips from its lattice point and occupies an interstitial site, thereby creating Frankel defect. So AGBR shows both Frankel and Schottky. So what happens in Schottky defect is that although the size between silver and bromide both is large and it can show Frankel defect, yet it has been found that in a crystal of silver bromide, silver and bromine together as pairs may be missing from the crystal. So since they may be missing, they may be completely missing, so we call them Schottky pairs. The pairs, the cation and the anion, positive and negative charge both together are missing. So such a defect where the cation and anion together are missing, they are known as such missing pairs are called Schottky pairs, and the defect is known as Schottky defect. In the case of Frenkel defect, zinc only moved from its place to an interstitial site, so it does not affect the density of the substance. But in Schottky defect, that is, if there is Frenkel defect, the density of silver bromide will not be affected because silver only moved from its lattice point and occupied an interstitial site. But if it was a Schottky defect, if it undergoes Schottky defect, the silver and bromide total, the silver and bromide ions completely are missing. One silver, for every one silver, one bromide is missing. So such pairs are missing. In that case, since they are missing, totally missing from the solid, the mass will decrease and therefore density will be affected, or density will also decrease. The same reason why density decreases in the case of a vacancy defect. So when you have Schottky defect is a kind of a vacancy defect, only the number of cations and anions missing is equal. Question 1.21. Explain how vacancies are introduced in an ionic solid when a cation of higher valency is added as an impurity in it. Explain how vacancies are introduced in an ionic solid when a cation of higher valency is added as an impurity to it. Okay, we can take an example. Cadmium chloride, it is there in the book itself, CdCl2 and AgCl. So you have a crystal of silver chloride and you add a little bit of cadmium chloride to it. The crystal is silver chloride, but cadmium has a charge of 2 positive, so it has a cation having a higher charge. Since cadmium has charge 2 positive and silver has charge 1 positive, if one cadmium is present, in order to maintain the balance of charges, the positives and the negatives, for every cadmium there should be 2 chloride ions, for every silver there should be 1 chloride ion. So if this is Ag positive, this is Cl negative, Ag positive, Cl negative, and that's the crystal how it is, Cl negative. Instead of Ag positive, if I get cadmium, then you will have 2 chlorides for it, right? And if there are 2 chlorides, then 1 silver should be missing. If 1 silver is missing, only then, like for 2 silvers, in place of 2 silvers, 1 cadmium will come. Because for every cadmium there should be 2 chlorides, but for every silver there should be 1 chloride. For this cadmium, if there are 2 chlorides, there should be no silver here. In other words, in order to maintain electrical neutrality, if an impurity with a higher charge is added, then it will replace those many cations in order to balance the charges. So explain how vacancies are introduced. So that is how this vacancy is introduced. There was no need of a vacancy if they were all silvers. But since cadmium has a charge of 2 positive, it needs 2 chlorides. 1 cationic site has to be empty in order to maintain the positive and negative charges, in order to maintain the electrical neutrality. So that is how vacancies are created. The next question is 1.22. Ionic solids which have anionic vacancies due to metal excess defect develop color. Explain with the help of a suitable example. You remember the example of sodium chloride crystal? Sodium chloride crystal, if you take sodium, this was explained in which topic did we do where I told you about the sodium chloride crystal? It was, metal excess defect due to anionic vacancies. So what happens if you have a crystal which has sodium and chlorine, if instead of Ag positive, imagine if these were sodium, sodium, sodium and chloride, chloride, chloride. On the surface, if you add excess of sodium ions, the sodium ions which come and settle down on the surface of the crystal, the chloride ions from the middle of the crystal are attracted towards the positively charged, the positive, it is not sodium ion actually, you just let sodium, neutral sodium, come and settle down over the surface. When that happens, the chloride ions close to it will have an effect on it and will try to convert it into Na positive. And it will successfully do it, thereby making the sodium loses one electron. And the chloride forms a sodium chloride and keeps the sodium. That creates an attraction due to positive charge and electrostatic forces of attraction. The positively charged sodium and the negatively charged chloride, they stay together. And therefore, the sodium kind of gets permanently stuck on the crystal. Now, the surface, the chloride on the surface, which has attracted it, a chloride from the middle of the compound will start moving towards towards sodiums that are coming and settling on the surface. At the same time, the anionic vacancies that are created as chloride moves to the surface are fulfilled by the electrons which are lost by sodium on the surface. Those electrons kind of go down and occupy those vacant sites of chloride ions, thereby maintaining the electrical neutrality, that is the positive and negative charges will still remain the same, but the anionic sites do not have chloride ions in them, now they have electrons. These sites are known as Farben centers or F centers, and they impart color. When you energize such a crystal, it imparts color to the crystal. So in the case of sodium chloride, that color is yellow. If you had a lithium chloride crystal and you carried out the same process, you would have got pink color. And if you have had potassium chloride, the color of the crystal would turn lilac due to those Farben centers which are created. So ionic solids which have anionic vacancies, the anion is a vacancy which is filled by an electron or as many electrons as are required for the neutralization of the charges, whatever is the charge on the cation. And all these examples are of unipositive charges. Sodium is 1 positive, lithium is 1 positive, and potassium is also 1 positive. So with the help of an example, you can take any one of these three examples, whether sodium chloride, lithium chloride, or potassium chloride. The next question is, a group 14 element is to be converted into an N-type semiconductor by doping it with a suitable impurity. To which group should this impurity belong? If the semiconductors are usually group 14 elements, they have 4 electrons in their outermost shell. To have an N-type of semiconductor, there should be more electrons, only then it will be negatively charged because electrons are negatively charged. To make it a P-type semiconductor, the number of electrons has to be less than 4 in the outermost shell. So, for doping to occur, you have to dope it with a group 15 element which has 5 electrons, 1 electron extra to make it an N-type of semiconductor. If the same question was about a P-type semiconductor, I would have said that you would have to dope it with an element of group 13. Because group 13 has only 3 electrons in the outermost shell, which is one less than 4 electrons, and therefore it would create a P-type of semiconductor. Basically, it's not positive, there's only a hole created, but since it appears to be positive, we call it a P-type of a semiconductor. The last question and the last thing that I'll be telling you in this chapter. Question 24, 1.24. What type of substances would make better permanent magnets? Ferromagnetic or ferrimagnetic? Justify your answer. We've studied about the magnetic properties of solids, and we know that ferromagnetic substances are those substances in which the electrons, they align themselves, or rather the domains, they align themselves completely in the presence of a magnet. The domains, all of them, they start pointing, they align themselves, the north and the south of the domains aligns itself to the affected or to the magnetic field to which it is exposed, or the magnetic field which is applied, all of them, all the domains, they align themselves. And even when you remove that magnet, the domains, they remain aligned. So that is a ferromagnetic substance. So once you turn it magnetic, it remains magnetic. So a ferromagnetic substance would make a permanent magnet. Why? Because its domains, once aligned, they remain aligned. In the case of a ferrimagnetic substance, on the other hand, the domains, first of all, not all of them align, only some of them align, and in the presence of a magnet, and when you remove the magnet, they again get disoriented, and therefore they lose their magnetic properties. So that would be the ferrimagnetic. Ferrimagnetic is observed when magnetic moments of domains in the substance are aligned in parallel and anti-parallel directions in unequal numbers. They are weakly attracted by a magnetic field as compared to ferromagnetic substances. Magnetite examples are given, and therefore when you remove the magnetic field, they turn paramagnetic and ferrimagnetic substances. That's why ferrimagnetic substances cannot be permanent magnets, while ferromagnetic substances are permanent magnets. So with that, we come to the end of this chapter. And the next chapter, that, as I told you at the beginning of the video, we'll be doing would be alcohols, phenols, and ethers. So if you found this video helpful, give it a thumbs up. If you wish to watch other videos of this chapter, click the link that appears on top of the video. And well, if you wish to learn more chemistry, come back to my channel, recommend it to your friends, and please do help me spread word about the channel, because if I can help any child score better marks or achieve their dream in future by studying chemistry, I would be very delighted to do so. Thank you for watching. Bye-bye for now.